Okay. Let's go ahead and look at number 8. Where did I put my pen? Oh, my pen up there. So number 8 is you also needed to convert 85 kilometers per hour. We're not going to necessarily do the whole entire thing, but it's a little bit different in thinking about solving this acceleration or this slowing down problem, because it's not necessarily slowing down over a traditional displacement of 0.8 meters. Basically, the collision is the car is compressing. It is crumpling inside of that, so that 0.8 meters is slowing down. It actually, we'll learn later in when we get to momentum and the impulse momentum equation, that it doesn't really matter how fast you're going when you collide into something like a barrier. What determines how much force you feel is how much time it takes for you to slow down. So, for example, in front of the bridges, you'll see like the like if we're looking at an overview of like a bridge or something like that, and there's this part here. They have those little barrels that are in front. What are those barrels for? So you're driving your car along the way. What are those barrels for? To slow you down. What do you think's inside of them?
Water.
It used to be water until they realized that water freezes and becomes ice. So they do use water. They just use water that has like antifreeze or is very briny. Sand is actually very hard to disperse, but those barrels are basically designed so that when you hit them, they explode apart and then they take the energy away from them. So yeah, so that's what that is. So the delta x here is that 0.8 meters, and it's not like I said a traditional like slowing down, but it is your car that is slowing down. To figure out how many g's it is, this is so 1 g is basically what you're feeling right now. You're feeling the acceleration of gravity of one gravity, which is what you're experiencing. If you're on a roller coaster, maybe experiencing 3 g's for a short amount of time, that would mean that your body's being compressed into the seat and you feel like you weigh 3 times as much you do. You can also have negative g's. You felt this if you've gone over a hill and you feel that weird like sense of almost brief weightlessness. You haven't?
Is it true that like a suction cup, like if he puts it down and like the force is pulling it back, like that's how heavy air is?
I don't think that's not how heavy. Well,
like if you stuck a plunger on the floor.
Because it's not the air that you're trying to pull up. It's the air pressure. It's the difference in air pressure around you. So, I mean, I don't think that's equal to all of the air that's in the air around you. It's a pressure difference. So. That's a good thing. I'll have to think about that there. So, so if you're trying to figure out how many G's you are, so if you have your value of what negative 348.41, basically you're just saying if I know 1 G is negative 9.81, the acceleration due to gravity, then how many G's is whatever the acceleration you're trying to find here. So once you solve for that, you just set up a ratio, cross multiply, divide. And that's where you get the 35.5 G's. And so that necessarily wouldn't be deadly. If we actually did calculate the time, we could calculate how much force was on there, but that's something for a second semester. But the crumple zone is extremely important because if this 0.80 was like 0, if there was no crumpling in your car, then your acceleration would be much, much, much higher. That's why when you hit an airbag, it's better. I mean, it basically explodes in your face because it has to open up really, really fast. But when your head hits it, the air deflates out of it, and so it slows down the rate at which you are slowing down. That kind of makes sense. So that's how we get to that. Let's look at number 9 and then number 10 together. It's not that number 9 is out of the question of you solving it. It's just in the past when I was like, hey, go ahead and solve it, we would have people all over the place, and it was kind of like herding cats to get people back to where we needed to be. So, in number 9, a car is moving at an initial speed of 100 kilometers per hour, so we're going to have to convert that. An accident happens in front of the car. The person driving the car takes 1 second of reaction time to react to the accident. I think that was an old. Before braking. The car brakes with an acceleration of negative 4 meters per second squared while coming to a stop. So I've actually split this up a little bit easier than the original version of this question because I'm trying to show you that this is actually a 2-part problem because if you were a number hunter, and this is like what a number hunter would say, oh, 100 kilometers per hour, that must be my velocity, and 1 second, that must be my time, and -4 must be my acceleration. But if you're not taking into context, there's actually two things happening here. There is the reaction, where you're just basically flying or cruising along, a reaction. It takes you 1 second to realize I need to do something and then brake, and then you slow down. So I'm going to draw a picture here at the bottom here to kind of signify what's kind of going on in this here. So we have our car, which is going along at CV. So CV means constant velocity. And before we do this, let's go up and actually convert 100 kilometers per hour into meters per second. So 100 so 1 kilometer is 1,000 meters. And then since hours on the bottom, I'm going to put hour at the top. So 1 hour is 3,600 seconds. Yeah, 27.78, I think. Is that what it is? Yep. So we want to cross out this 100 kilometers per hour so we don't even have a chance of using that. So 27.78 meters per second. So once again, the question, do we use this rounded value or do we use the value that's all in our calculator? Just use the rounded value, because everybody's calculator, you can actually set it up to go out to like 20 decimal points or go out to 4 decimal points. So we'll just go ahead and keep that there. So we're looking down back at our picture here. The velocity of this car is 27.78 meters per second. And it's doing that, you're not even braking, you're just like, in the moment, before you even touch that brake, you're still going that velocity for 1 second. So that's basically the first part of the problem. Then when you realize that you actually need to hit the brake, this is constant acceleration, so CA. So this, you are now slowing down. And so once you are slowing down, once you have constant acceleration, now we're into our 4 equations. So here, these are the 1, 2, 3, 4 equations for slowing down. Here we only have the one and only equation that we have for constant velocity, which is next to the 4 equations. If you can't see, it might be on the actual whiteboard up there. So I'm going to go ahead and kind of solve this. Let me find my work here. I'm going to split up the work so I make sure I'm not getting too kind of confused here. So I'm going to write up here, first we're going to take a look at the reaction. Okay, and then later we'll look at the braking. So we should realize now that the 1 second has nothing to do with the actual braking part. It only has to do with this. So our equation for velocity, constant velocity, is displacement over time. And we're trying to solve for displacement. This is what is the displacement during the reaction time. So our equation is delta x equals v times t. And we already know, we already just calculated that it's going 27.78 meters per second for 1 second. So how far does it travel during the reaction time? 27.78 meters. So even if, this is kind of interesting, I mean scary in some instances, but even if you had some kind of amazing technology where you could stop, the moment you stepped on the brake, your whole car stopped immediately. It would actually be very, very bad for you, because you would keep flying forward at 27.78 meters per second and slam into the windshield. But let's say it was perfect enough that everything inside stopped. Because of that reaction time, you would still travel almost 60 feet before you even hit the brake. Yeah, Evan? What do you mean?
Like, why did you do 27.78?
Because this is the constant velocity equation. This isn't one of the 4 equations. You see there's an equation that's written to the left of the word save up there on the board.
Yeah.
So this is our constant velocity equation. There is no 1/2 associated with that. Yeah, you may see it. You may see a similarity between the first equation there and the constant velocity. So those equations can't be used together. So this is the only equation we can use, because it's telling us that we are traveling 27.78 meters every single second. So that's how far, that's basically part A, that's how far you're moving before you even hit the brake. And then once you start braking, this is basically like the other problems that we've had on this worksheet here. If you want, you can go ahead. We can go ahead and write stuff in these boxes over here. So now we're dealing with this. So we're trying to figure out what is this displacement. What's the initial velocity? Yep, 27.78. That's exactly how fast you were going before you hit the brake. It says that you're coming to a stop. Remember, 2 means the final, so that's 0. And they don't give us the time, but they do tell us the acceleration is -4, which is not really that severe of acceleration. So if we're looking at which equation, go ahead with your hand on which equation 1, 2, 3, 4 of the 4 equations we have. And for those that are listening on this video here, I'll put the 4 equations online. Yes, it is the 4th equation. But we don't have time, so VF squared equals VI squared plus 2A delta X. Go to plug things in. 0 squared equals 27.78 squared plus 2 times acceleration -4 delta X. So when we square this 27.78 squared, obviously it's going to be a bigger number, but then in order to solve for delta X, we have to subtract that. So we're going to get a negative 27.78 squared. And then that negative, basically, that's going to be on the left side of the equal sign is going to cross out with this negative in our acceleration. And our delta X is going to come out as a positive answer, which makes sense. I mean, you're traveling in the positive direction. Yes, you're slowing down, but you should have a displacement that is positive. It wouldn't make sense if it was negative. So 27.78 squared divided by 2, divided by 4, 96.47 meters. So that's how far traveled just in the braking. Questions? Anybody have squinting eyes, understanding where that number came from? Yes.
When we're like solving the equations and like throwing our work, do you want it to like put like units in there?
You don't have to. I mean, I kind of don't, because sometimes it gets pretty heavy, especially in some of our equations. If you want to, you can go ahead and do that. I'm fine with you, as long as you know what the unit should be when it pops out of there, I'm fine with you not having to necessarily put it in there. I mean, sometimes I include it, but not necessarily. So once again, I took 27.78, I squared it, I just subtracted it over to the left side, so it became a negative number. That negative number and the negative in the 4 crossed out. So essentially you have 27.78 squared divided by 2 divided by -4. And so the part C here, it's asking what's the total. Well, the total is just adding those two numbers together. So 27.78 plus 96.47. 124.25. Another thing to notice that when I calculated this 96.47, I didn't do any internal rounding when I was calculating this equation. I basically kept everything in my calculator until I got to the part where I was actually solving for it. So there are going to be sometimes little differences there, but if you're basically, unless you're just doing some outrageous rounding, you should be within a tenth or even less from where we are. So 124.25 meters is the total distance. So now that's a pretty long ways. You may say, well, that's like considerably longer than a football field there. So you know, why is it taking that long? Well, -4 meters per second squared would almost be like if you saw like a crash or something going on a mile away, and you saw flashing lights. And -4 might even be if you just took your foot off the accelerator and let just the air resistance slow you down, or it might have been minor braking. We didn't calculate the time. If we did calculate the time here, we'd probably see that the time would be probably pretty long time for it to slow down. So actually we calculate that? Yeah, 27.78 divided by 4. That's not right.
Is that like 6 or 7 seconds?
Yeah, it's like 7 seconds. So 7 seconds to slow down is, I mean, we're hoping that if you see a crash a mile away, you don't just slam on your brakes and cause a 30-car pileup where somebody else is going to have to do this calculation to figure out how far away they are. So that's number 9. Okay. Oh, is the internet back? The internet is back. I am whole. Okay, let's do number 10. So number 10 is not saying that it can't be done. That's why when Reese told me that he got number 10 done yesterday, I was like, not that I've never seen anybody get it done there, but it takes there's basically 2 pieces of information that have to be known and understood for this to even be possible. So I'm going to kind of show it, not necessarily the long way. I mean, you can write it shorter ways, but understanding why you're doing certain things. So let's go ahead and read through number 10 here. As a traffic light turns green, a waiting car starts with a constant acceleration of 6 meters per second squared. At the instant the car begins to accelerate, a truck with a constant velocity of 21 meters per second passes in the next lane. How far will the car travel before it overtakes the truck? Because remember, the car is not moving in the beginning, the truck's already flying by. And then also, when the car eventually catches up to the truck, how fast will it be going? And this is an interesting situation. Basically, the car is sitting there waiting for the green light. And what's happening with this truck is like 21 meters per second is about 45, 50 miles per hour. The truck is just gunning it towards this red light, hoping that the moment it crosses the line where the car is, it turns green. So I guess to each their own, whatever. So because if it didn't turn light, he would just go 15 miles per hour into a 4-way stop. So before we do this, I think it's helpful to look at this graphically on a position versus time graph, because this is going to give us our secret behind making this problem even possible. So we have position versus time. We're going to try to make a sort of a conceptual graph of what the truck and the car would look like. So first we'll look at the truck. The truck is going to have a constant velocity, so on a position versus time it's going to be a straight line. And so we'll go ahead and make it something like that. So that is the truck. It should be a straight line. That is the truck, and that is a constant velocity. So if that's the truck at a constant velocity, what would it look like for the car it was accelerating? Yeah, I don't know if it's technically exponential, but yeah, it is a curve that it's upwards there. So it's going to be flat in the beginning, and then it's going to speed up at some point. So go ahead and do that here. Okay, something like that. And so that is the car, and that is constant acceleration. Understanding what's happening right at that point where they basically are passing each other is the whole clue to this. So there's 2 things about what's happening here. What is happening? The car and the truck are at the, if this means position, what does that mean? They're at the same position, right? At that time? At the same what? At the same time. Their position and time are equal to each other. Nowhere before that, nowhere after that is that the case. But at this, and if you think about it, that makes sense. In order for the car to pass the truck, at that moment, they're right next to each other, and they've also been moving along since time began at that same point. Now, they're not going the same speed. You can see the slope of the car here is steeper than the slope of the truck, and we'll actually see something interesting I was alluding to Reese earlier. So we're going to go back up here. I'm actually, because we have a couple things going on, I'm not actually going to use this. But let's go ahead and split this up between looking at the truck, which is constant velocity, and the car, which is constant acceleration. So constant velocity, we can only use that basically v equals x over t. And constant acceleration, sorry, that's not x over x, that's x over t. And then constant acceleration, we can use any of those 4 equations over there. Before we do that, let's kind of recognize some stuff right here that's going to make our life a lot easier. So the position of the, so I'm going to go ahead and leave out the delta here just to try to make it a little bit shorter. Position of the truck is equal to what? It's equal to what position of what? The car. So the position of the truck is equal to the position of the car. So there's no need to actually write out position of truck, position of car. We can just call that X, which is really, really nice. You're going to see in a second how insanely complicated it would be if their position and their times were the same. But also, let's go ahead and talk about it. So the time of the truck, as we can see down here, should be the same time as the car, because they both basically took off or were, when it turned green, the time started for both of them. So that tells us that we can just talk about time. That understanding right there makes this problem possible. So let's first look at the truck, and we're going to try to figure out an equation that has both position and time, because that's the two things. They have different. The truck has a velocity, the car has an acceleration. They're different. But the only two things they have in common are the position and time. So let's go ahead and look at the truck. I'm going to write out the constant velocity equation using all the variables, and we'll simplify it. So what we should see here is that the velocity of the truck is equal to the position of the truck divided by the time of the truck. Now, we know that position of the truck and the time of the truck, we don't need to specify those, so I'm going to rewrite it here, that the velocity of the truck is just the position divided by the time. The reason I wrote out the first equation is just when we see the car, we basically would have like 8 unknowns in 2 equations. So now we know this. We don't know the position, we don't know the time, but we do know the velocity of the truck, and that is 21 up here. So we're going to go ahead and plug in 21 equals x divided by t. Now, I should have talked about this a little bit earlier. We're trying to figure out how far and how fast, but it's very, very helpful, actually, and this just in general for problems we're going to be working on later, that even though it doesn't ask us to solve for time, solving for time is extremely important, and it's actually going to make doing this problem easier in the long run. And all that. So we're actually going to choose to solve for time first, but in order to do that, we're actually going to solve for x here first, and you'll see in just a second while we're doing that. So rearrange this so that we're solving for position. So we do that, displacement is 21t. So it may be confusing. You say, well, we're solving for time, but why are we solving for position? We'll see in just a second here. So that's as far as we can go. We have 2 unknowns in one equation, and for 2 unknowns, minimally how many equations do we need? 2. So the car hopefully will give us an equation over here. So first of all, let's think about what we know about the car. Okay, we know, not necessarily we know about the car, but we're trying to figure out. We need to figure out the position or the displacement of the car, the time of the car. We know the acceleration of the car, and we know the initial velocity of the car. We don't know the final velocity of the car yet. So looking at the 4 equations over there that we have, which equation basically has all 4 of these in some manner? So use your hands of which one has all the ones that we're talking about. Should be the 3rd equation. Yep. We don't have the final velocity. That's actually what we're trying to find. So I'm going to rewrite the 3rd equation. I'm going to write out all the variables in here, and we'll show how complicated this would have been. So if we didn't realize this. So what this says is that the position of the car would equal the initial velocity of the car times the time of the car plus 1/2 times the acceleration of the car times the time of the car squared. You can see how complicated. If we didn't realize that the position of the car and the truck were the same, we would have this equation over here and this equation over here, and we would have 4 basically. We'd have 4 we'd have 4 unknowns with 2 equations, and that wouldn't be possible. So let's go ahead and rewrite this. Before we do that, what is the initial velocity of the car? It's just sitting there at the light. 0. So that makes this whole value right here 0 times the time, which is 0. So we'll go ahead and really position the car is just x because they're the same. 1/2, because that's 0, times the acceleration of the car up here, which is 6, so 1/2 times 6, times the time of the car, which we know is the same as the truck, so it's just t squared. Now I said we're trying to solve for time. Why is it that I set up the equations to solve for x? Yeah.
So you can plug in 21t from the...
Yeah. We know these are the same, so basically we have two equations, two unknowns. It's called system of equations. You can call it substitution. But by solving for x and plugging these two together, we eliminate that unknown variable until later when we want to solve for it. Okay? So let's go ahead and plug these two together. We get 21t equals 1/2 6t squared. Now I'm not sure if I mentioned this. The reason I'm probably not going to have this on a quiz as traditional points. You're like, why should I pay attention? Because sometimes I'll put problems like this as extra credit, and so if you pay attention, you understand how these are really supposed to go, then you'll have a much better chance at the extra credit. Good. Let's go ahead and simplify this. We can cross out that t with this squared. So 21, and we can say 1/2 times 6 is just 3t, or t is equal to 7 seconds. Because if we had solved this another way where we didn't solve for time, we'll check here in a second. So we're trying to figure out how far the car will travel. So which equation should I use to figure out how far the car traveled? Does it matter? Does it matter if I use this one or this one? Why? It doesn't matter. Why? Yeah, you were going to say that? They're the same position, right? So here's our check. Here's our check. If these two answers don't equal the same, then we're basically saying that they don't actually pass each other at the same time. So these have to match the same. So let's look at that. X equals 1/2 times 6 times 7 seconds squared. And then this says x is equal to 21 times 7. 1/2 times 6 times 7 squared, I think, is what, 147? So that's good. 21 times 7 is also 147. So it's rare in problems that you can walk away from there realizing that your answer is correct. So that is the position. So that's kind of like, hey, if you didn't have the same answer there, then this time is wrong. So once again, you may say, like, this is a really long problem. Obviously, from now on, you'll realize that you don't have to write it all out here. I'm just showing you how complex it would have been if we didn't make that connection up here. Then the second part, how fast is it going? So here we're talking basically about the car. This is constant acceleration of the car. So we need to pick one of the four equations to figure out how fast the car is. Basically, we want to know what is the final velocity of the car when we know what's the initial velocity of the car? 0. We know the acceleration of the car is 6, and we know the time that it took to accelerate is 7 seconds. So which equation will we use to figure out that? Second equation, right? Nice second equation coming in to help everybody else out. Initial velocity here is 0. That makes things nicer. So the final velocity of the car is equal to basically its acceleration times the time it was accelerating. So acceleration, time, and the final velocity of the car comes out to 42 meters per second. Now, I had asked Reese at the beginning of class here, is there any, and I'll ask you too, we have 42 meters per second, which is the velocity of the car, and the truck had what velocity? 21. The velocity of the car is double the truck. Will that always happen? Yes. That will always be the case. It doesn't matter the acceleration. It doesn't matter the velocity. As long as the car starts from rest and as long as the truck doesn't speed up or slow down. So basically, as long as we have this situation here. Now, it's not quite obvious to see where that comes from. Evan, you actually asked that question in the beginning. I think about number 9. You're like, why aren't you doing 1/2 for that? Well, in the acceleration equation, this 1/2 that is right there is basically the reason why that is doubled. To show you why that is the culprit or the reason is, let's say we get rid of this 1/2, just hypothetically. If we got rid of this 1/2, then the velocity of the car should be 21. So let's see that. So if instead of, this is my calculator, my old school calculator, okay, instead of 21 divided by 3, we did 21 divided by 6, okay, that's 3.5. Okay, and if I took that 3.5, which is my time, and put it down here instead of 7, 6 times 3.5 equals 21 meters per second. So it's, there's more kind of in-depth mathematical reasons why that is, but it's, now here's the thing, you're saying, well, if this is an extra credit problem and you have a new problem and you say the truck is going 10 meters per second, you can't just say, oh, the car is going 20. You have to show me something what's going on. It doesn't necessarily have to be as involved with this, but basically creating your two equations and showing me not only is the time, but also the position should be the same, but that as well. So it's kind of an interesting problem thinking about that. And if you don't believe me that it's always going to be the case, just change any of these variables, and if you change that to 10, it's going to basically change the time. It's going to change the position, but it'll work out that the velocity of the car will always be double the truck. So that's not the last thing we're talking about. One last thing we're talking about, if you could actually put this in your traditional notes. So just because you guys are going to eventually turn in this packet, I want you to have this here. So speed up or slow down. We're going to look at 4 scenarios here where an object is either speeding up or slowing down. And this is actually a correction of a major misconception in physics. Okay, so we have four nice looking cars here. Nice thing when we get to drawing forces and free body diagrams, that you don't have to necessarily know how to draw something. You want to see a nice horse? There's a horse. Okay, you want to see a car? There's a car. I'm actually really bad at drawing horses. I know what a horse looks like. Yeah, but okay. So let's try. Let's try one horse real quick. Okay, so you can only use one line. You can't pick up your pen. Oh no. This is not bad. This is going. This will be going in. Oh man. That's actually not bad. That's actually getting better there. So, well, I need to. That's a horse. So that's why I use that as a horse. Just wait until we get to the problems where I have to draw a flying squirrel. It basically looks like a squirrel that looks like a cat that has airplane wings, and so. Anyway, so we want to know whether something is speeding up or slowing down. The biggest misconception is, and it unfortunately kind of comes from this packet, because all of this packet, the objects have been moving in the positive direction, which is to the right. So traditionally, or up and to the right are positive, and down and left are negative. So everything in this packet, just kind of for ease of this, people are like, why is there a horse in here? But, maybe this should be my thumbnail right there, so get people interested in that. So anyway, there's like, hey, if it has negative acceleration, it must be slowing down. That's basically what was happening in this problem. Well, let's look at 4 different scenarios and try to argue whether or not that is always the case here. So this first one is moving to the right. So when you see positive velocity, it's basically telling you it is moving in the positive direction. That is that is basically its initial state. It is moving to the right. But if I have a negative acceleration, remember this doesn't mean less than 0 acceleration. This just means my acceleration is in the negative direction. We'll learn later with Newton's second law and forces that if you have an acceleration, there must be a force present. So maybe like braking or air resistance or something like that. So if you think about this like you're traveling down the hallway or something like that, and somebody's pulling in the opposite way against you, what's going to cause you to happen? Speed up or slow down? You're going to slow down. So you may say, okay, well, you're slowing down. You're moving towards the right. Why? Because you were moving towards the right in the first place. And so the misconception says, oh, negative acceleration always means slow down. You can't just look at that. You have to look at the initial conditions as well. Why was a negative acceleration slowing down? Because the velocity was in the opposite direction. Whenever they're in opposite directions, you're slowing down. Let's look at another case here. Let's say you're once again moving in the positive direction, and your acceleration is also in the positive direction. These are probably the ones that we're most familiar with here. So you're moving towards the right. This would be like walking in the hallway and somebody's pushing you in the same direction. What's going to happen to you? You're going to speed up. So you're basically speed up, but you're moving in the positive direction. Okay? This may cause you to think, okay, negative acceleration always means slow down and positive acceleration always means speed up. That's not the reason. The reason this was slowing down is because they were in opposite directions, and the reason this is speeded up, they were the same. So let's look at two other different scenarios here. Let's say you're moving in the negative direction, so you have a negative velocity, not less than 0, you're just moving to the left now, and your acceleration is positive. You might be saying, you might be saying that positive acceleration means speed up, but what's happening here?
It's slowing down because they're in opposite.
Yep, they're slowing down because they're in opposite direction. So that's why we don't like using the word acceleration, deceleration, because it kind of doesn't really give you direction. This would basically say you're slowing down because you're accelerating in the positive direction. So this would mean that you're slowing down. And which way are you moving? You're moving to the left because that's the way that the velocity was initially moving. Okay, so basically opposite directions. It's sort of like, hey, one friend wants to take you this way, one friend wants to take you this way, and you're being pulled in opposite directions. It's going to slow you down as opposed to both friends agreeing with each other and pushing you in the same direction. So the last scenario here is that you're going to the left, you have a negative velocity, and you have a negative acceleration. People that are ignoring this whole entire lesson basically look at that and say, oh, negative acceleration, slowing down. But you are already moving to the left, and you have an acceleration that is also to the left. So this one means that you are speeding up because they're in the same direction. You're speeding up to the left. So that's why context really matters. So don't always assume. Don't say, hey, negative acceleration slowing down. Don't always assume that we're moving in a specific direction. That's why you have to take into account context. We'll see some different problems where we're moving to the left, or especially when we're moving down. Let's say we look at, for example, why does a ball, when you throw it up in the air, why does any object, when you throw up in the air, why does it slow down? Why does it speed up? So if you have the ball and it's going upwards, the reason that it's slowing down is you have the acceleration of gravity downward, but the ball is initially going in this direction. And so even though you have a negative acceleration, it's an opposite direction, so it's slowing down as it moves its way up. It then gets to the very top, gets to the very top here, and then starts moving its way down. The acceleration is still down, gravity is always still down, but now the ball is starting to move in the down direction, so it has a negative velocity. The fact that these two are in the same exact direction means that it is speeding up. And we'll talk about other stuff about what's happening at the very, very top later. One last little kind of thing to add on here is just to be kind of complete. Yes, you can speed up. Yes, you can slow down. But the third way in which you can accelerate is what? Remember? Yep, change direction. Isn't that what you were going to say? So let's say that you had a object here, and we'll just look above it, and it's moving in the, let's just say, we'll call that positive direction, or has a velocity this way. But its acceleration is, let's say for this example, is in this direction, or negative acceleration. Okay, because remember, down means negative. In this case, what would happen to it is it would cause, well, we'll do vectors later, but basically it's going to cause this thing to want to travel in a circle as it comes back around. We have this acceleration that is facing the center. That's what we call centripetal acceleration, because centripetal means center facing, and so that's what's causing it to turn. Let's say this acceleration is caused by, it could be brakes, or it could be friction on the road. It could be spinning something above your head, and that's holding. Let's say that suddenly this acceleration went away. What would happen to your vehicle or object? Just going to go straight, right? Because that's the direction it was already moving. So that's a lesson for later times. But yeah, because you're accelerating, you're constantly turning, and that acceleration is what's causing it to do that. So that basically wraps up sort of what we're doing here today. So